Okay, so let me get started maybe. And I realized that I had made a rather ambitious plan for the last lecture of a very long day. So let me try to say what I intended to say using more examples. I will maybe state some results, and we have a tutorial session tomorrow afternoon where we can try to work out some of the proofs or the details if you're interested. Okay. So the first half an hour or so, I want to sort of complete something which I left hanging in the morning, which is entropy. So I want to discuss entropy for a little bit. In particular, I want to talk about the entropy associated with a quantum state rho, which, as you know, is a positive trace one operator, which covers the entire set of states that we would like to talk about, whether pure or mixed, right? Okay, one more small aside. I said something about convexity in the morning. Maybe I should say a little bit about this. So, imagine I take two density matrices, rho 1 and rho 2. They are two states representing the same system, different systems, whatever, right? Let's say I make, again, this convex mixture of these things, which means I write down some p times rho 1 plus 1 minus p times rho 2, and I call this some sigma. Okay? I hope it is easy for you to see now that if rho 1 and rho 2 are valid states of the system, meaning valid density operators, then so is sigma. Okay? So sigma is also a valid density operator. So this tells me that the set of all density operators forms what we call a convex set. Okay. Meaning I make these convex combinations of elements of this set and I get back elements of the set, right? And I can also now have a notion of the extreme points or the extremal points of this set. What would those be? I'm saying you consider the set of density operators, you make combinations of them, you get other density operators. What would you think of as the extreme points of this set? Pure states. What do I mean by extreme points or extremal points of the set? Those are the operators or those are the states which cannot be decomposed any further, right? And those are your pure states. And all states in the set can always be realized as convex combinations of points in this extremal set, okay? So these are your pure states. I want to say that in the case of the two-dimensional quantum systems, which we like to call qubits, this has a nice geometry to it. Your extreme states live on the boundary of a sphere, and all your other density matrices live inside this sphere, right? And this very nice sort of boundary and interior sort of geometry happens for the case of qubits. And many of you may know this as the Bloch-Poincare sphere and so on, okay? So just wanted to point this out. Okay, this was an aside which maybe should have been said in the morning. So let me get back to now talking about entropy. Now, with a quantum state rho, I can associate two kinds of entropies, okay? So someone said, what is entropy? So what do you mean by entropy? And the answer I gave was a somewhat information theoretic one. I said it describes your state of knowledge, or complementary way it describes the state of ignorance of the system, right? And how do I extract information about a quantum state? I measure, right? I could perform measurements of different observables on this state, get different probability distributions that come out of it, and using that information, I try to reconstruct the state in some way. That is one way of thinking about, or I may not even want to reconstruct the state. I may just want to know what is the expectation value of some spin observable in this state. That is the information I wish to extract. But even to do that, I need to perform measurements. So when I perform a measurement, so one is what I call a classical entropy that I can associate with the state. I say classical because I perform a measurement. The measurement induces a probability distribution, and then I can talk about the entropy of this probability distribution using any of the measures of entropy that I would think about in the classical setting. So this is some probability distribution. And of course, the standard measure one may use in the classical case could be the Shannon entropy, right? People familiar with the notion of Shannon entropy here? Yeah, it was also mentioned in the morning, I think, in the context of Boltzmann and so on. So I'm going to use the notation H to denote the Shannon entropy, to distinguish it from what I'm going to write there, which is a quantum entropy. So this is sort of my notation for this. So the definition is, of course, minus sum over pi log pi. So you can think of this, as was pointed out in the morning, as negative expectation value of log p, or log of the probability distribution, right? Or in other words, you can think of this as expectation of log 1 over pi. Okay, and this is how Shannon defined it in his paper, where he spoke about this log 1 over pi as constituting the degree of surprise in the realization of a particular event whose associated probability is pi. So you can think of it this way. So if the probability of a particular event happening is 1, then you don't gain anything when you know that that event has happened, right? Because this anyway had probability 1, so your degree of surprise is the lowest, right? Whereas if there is a very low probability event which is realized, then your degree of surprise is much higher. So in a very loose sense, the amount of information you gain from a particular event or a particular outcome happening is sort of inversely related to the probability of that event or that outcome. And so 1 over pi you can think of as the degree of surprise, while log, well, I think the argument there was that you needed this to be an additive sort of function, that if I have two different events happening, each of which with a different degree of surprise, then the amount of uncertainty or the amount of knowledge is now added up somehow, and that's where the origin of the log function comes in some way. And then if you want to know, I have a set of possible outcomes, what is the average uncertainty in this process, or what is the average information that one extracts from this distribution, then you average this log 1 over pi function and you end up with this entropy function, okay? So this is one way to think about this Shannon entropy, and in our context, this pi is nothing but the probabilities that I will write down based on something like a Born rule, right? I am starting with some state, I measure some observable, I get some set of probabilities, and I can write down a Shannon entropy associated with that probability. Now you can go back to the examples we did in the morning. If I am already in an eigenstate of an observable, right, then I do not gain any information by measuring this, because I'm already in a state of certainty as far as this observable is concerned. So then the resulting probability distribution is basically just a delta distribution. It has only one outcome occurring with probability 1, all the other outcomes probability 0, and that is the case where this entropy vanishes, right? You can either say that you gained no information from this, or you can say that your state of uncertainty about this is 0, okay? So one limit of this is of course 0, and the other limit of this is, yeah, let's say I goes from 1 to D. What is the maximum value that this entropy can take? The uniform distribution. What are these probabilities in the case of the uniform distribution? 1 by D if I have D possible outcomes. So this is log D. Again, we go back to the spin observable example. If you're in an eigenstate of X and you measured Z, you know that the X eigenstate is an equal superposition of the Z states, right? So when you perform that measurement, what you end up with is in fact a uniform probability distribution, right? And in that case, the entropy that you would associate with this combination of state and measurement will be the maximal in that case, right? So there is a way to prove this more rigorously mathematically that this is an upper bound. I'll indicate this argument for the quantum case because I'm just going to next talk about the quantum, the von Neumann entropy. So getting a classical probability distribution out via measurement and then writing down the entropy of that distribution is one way of talking about the entropy associated with a state. I could also instead directly talk about what I'm going to say call a quantum entropy, okay? And let me define this here. So this is the so-called von Neumann entropy. And this is an entropy which I will define by analogy with the Shannon definition, okay? So I will again take the log function, except I'm going to now take the log of the operator itself, okay? And then take the trace of this. So negative trace rho log rho is how I'm going to define, is how the von Neumann entropy is defined. Now, this seems like a somewhat strange object if you haven't seen or worked with this before. So let's try to break this down a little bit. How do I compute something like log rho? What do I mean by log rho? How would I compute these kind of operator functions? Exactly. So think about the spectral decomposition of this operator. And then if you can diagonalize the operator, then you can write down the log of this operator. You can write down trace rho log rho, etc. So once I have the spectral decomposition, I have a nice form for the von Neumann entropy, which would be what? Exactly. So this would just be minus sum over I, EI log EI. And remember, this is a density matrix. So this set EI actually constitutes a probability distribution. These are the eigenvalues of a density operator. So the von Neumann entropy of the density operator is simply the Shannon entropy of its spectrum. Okay? So this, in a sense, is what motivates this definition. You can also think about it as, in the classical sense, an expectation. Remember that if I were to compute, so if I want to think about the expectation value of some observable A in state rho what would that be? Yeah? So you're essentially doing the same thing here. You're again computing the expectation value of the log with respect to the density matrix rho itself. Right? In the same spirit, you can think about the other entropy that I defined in the morning, which is the linear entropy. So someone asked me, why linear? And there could be two ways of thinking about this again. So this linear entropy, is it in any way related to this von Neumann entropy? So the way I defined this, if you remember, was 1 minus, trace rho squared okay. So one way to think about this is you expand this log function, you do your standard series expansion for the log and you keep only the linear term, okay? And then you will see that up to the linear approximation of the log, this is what you get. So this linear entropy is basically, one way to think about it is a linear approximation of this von Neumann entropy. In the classical sense again, you can think of this, if I write this down again in terms of the spectrum of this evaluates to what? So what would this be in terms of the eigenvalues, just like how I had this form of the von Neumann entropy? Yeah? EI squared. So this classically is called a collision entropy for the probability distribution EI. Some of you who look at things like random walks and so on might have seen something like this. 1 over this is sometimes called an inverse participation ratio in the context of information spreading or state spreading over multiple sites and so on. So this is related to something called a participation ratio or an inverse participation ratio. And you can then think of this without the 1 as the expectation of EI itself. And so you're taking the expectation of a linear function and hence the name linear entropy also. I should thank Professor Jayakumar for pointing that out. But I just want to point out that this is not very unrelated to that notion of entropy. They are all, I would say each of them captures different things operationally, right? And the linear entropy is also something nice because you see, I can easily compute trace of rho squared, whereas if I want to compute this, as someone said, you first have to diagonalize this density matrix. And when I have a large many-body system, I may not be able to really do this. It's computationally maybe inefficient to do this, but this is something that I have a very nice computational handle on and much easier to compute, okay? Okay, so let's look at the von Neumann entropy a little more closely. Yeah. Yeah, I'm going to talk about that, yeah. Because I've not yet come to bipartite systems. When I do that, indeed, we will talk about the additivity of this. Okay. So does this von Neumann entropy also satisfy sort of the intuition that we have that if I have a pure state, then I have complete knowledge of the system. So I expect that its entropy must be 0, right? So I'm going to say properties of S of rho. So if my rho is of this form, then the entropy is 0. Is that something I will leave for you to check, okay? And if you're having difficulties, then we'll discuss this during the tutorial tomorrow, okay? I'm going to say this very often over the course of the next 1 hour. So of course, this, sorry. The question now is, what is the maximal value that this can take? Okay? Sorry, no, I wanted to say general density matrix, okay? So you can see that it's always positive just from the way the function is defined, okay? And the lower bound, which is the 0, is attained for pure states. So what is the maximum value? Since you see that this is the Shannon entropy of the eigenvalue distribution, so you expect that this should be log D for a d-dimensional, for a density matrix on a d-dimensional system. Is there a state that is going to attain this maximum? Sorry? Bell state. I'm talking about a single quantum system. There's no role for Bell yet. So the state that is going to attain this log D, again, by analogy with the classical case where you told me that the uniform distribution is the one that is going to attain the maximum Shannon entropy, what this means is you expect that these eigenvalues are going to be uniformly distributed. So essentially, if I write down a spectral decomposition of the state, I expect that it is going to be of the form 1 over D, oops, right? And it doesn't matter what these eigenstates are. And this is the state which I referred to in the morning as a maximally mixed state. So the von Neumann entropy attains its maximum value for a maximally mixed state. And this is a state about which my state of knowledge is the least, or my entropy is the uncertainty is the maximum. So when I gain knowledge of the state, I gain the most, right? So that's why the entropy is maximum here, whereas with a pure state, I have an exact description of the state. Now, we kind of intuitively put these upper bounds and so on, but there's a nice mathematical way of showing this both in the classical and in the quantum case, and that involves defining something called a relative entropy, okay? Have people seen this before? Some of you have seen the relative entropy. Okay, so in the classical case, the relative entropy is, okay. The relative entropy is also often called a divergence, the Kullback-Leibler divergence. It can be thought of as a distance measure between probability distributions, right? So I'm just going to call both of them relative entropy, the classical and the quantum case, okay? So in the classical case, you consider two probability distributions, some Pi and Qi, okay? And it's written like this with a pair of lines in between to say that this gives you some kind of notion of distance between probability distributions. And let me just write down a definition for this, and then we'll extend the same thing to the quantum case. So this is defined as sum over I, Pi log Pi minus Pi log Qi. So I'm just simply going to write it like this, okay? This is a very useful quantity to know and study, both in the classical and the quantum case. And it can be shown that this entropy is always positive, as it should be if it's a distance measure, right? And the positivity of this relative entropy can be used to show that the maximum of the Shannon entropy is essentially log D, and that the state that, or the distribution that attains it is the uniform distribution. Now, analogously, in the quantum case, I can again define a notion of distance between a pair of density operators. Okay? Now, because now we are talking about operators on a space, we have to be a little bit more careful with the definitions. So we will have to add some caveats here, which I will when I define this. So I'm going to say this is trace rho log rho minus rho log sigma. Okay? Now you realize that if, so this definition could run into some problems. If the, if your rho has support on the null space of sigma, because you're doing a, you have a rho log rho minus a rho log sigma, right? So it kind of implicitly assumes that you are not going to have to worry about the null space of sigma. And that is true only if the support of rho, lives within the support of sigma. Okay, so this definition holds so long as the support of rho is within the support of sigma. Otherwise, you have to kind of say that this blows up and so on, right? Yeah.
So, from the definition, as we can see that in the first definition also it is given pi log pi minus pi log qi, and here also rho log rho minus rho log sigma. Why one didn't think about pi log pi minus qi log qi or rho log rho minus sigma log sigma? Why let's place them somewhere?
That is just the difference of two entropies. No, what you're talking about is you're asking why is it simply not.
So that can't be a relative measure of entropy if we think of, like we think about relative velocity or something.
So when you already take out the entropy, right, it's a single number that you're getting out of this distribution, right? But when I want to compare two probability distributions, I want to be able to compare them element-wise. So if you think about what this is doing, this is comparing log pi with log qi and then taking an average over that. So you can think of this as average of log pi over log qi.
But why there is only pi? Can we have qi also there?
So you have to then take the other way around, right? So this definition itself is not symmetric. Right? There are other symmetric measures that one can think about for comparing two probability distributions, right? But if I were to define it the other way, so there are some people who define what's called a symmetrized divergence, where they take this plus the other way around, which is qi with pi, right? And you can write down, I think that's called a Jensen-Shannon divergence, if I'm not mistaken, right? But here I'm just introducing it more as a tool for you to be able to show these properties of the entropies, right? But you can symmetrize it by putting the other way around, and here again you can do that. You can think about S sigma rho, and then you will have the other way around, right? Yeah, so I think that's called a Jensen-Shannon divergence, which is also used in various probability calculations. So that that doesn't matter actually. So long as, I mean, you have two distributions and you order them in whichever way you want, right? That doesn't matter.
Also, this entropy equal to 0 means that both the
Exactly, yes. So thank you. So when this divergence is 0, that tells you that the distributions are identical. Right? So the property of this entropy, which I was coming to, which is useful, is the fact that it is positive and the equality, yeah. So that's why I said it is like a distance. So let me just write this for the quantum case. So the quantum relative entropy S of rho sigma is always greater than or equal to 0 with equality if and only if rho is equal to sigma. Okay. Now this is something that I'm not going to prove. This is called Klein's inequality. So I think people were asking me for references which I should have done, provided in the morning itself. So a lot of the discussion comes from this book by Nielsen and Chuang. But of course the information is spread out in different places. So chapter 2 has a nice discussion on the density operator framework, which I discussed in the morning, measurement, density operators and all of that. This discussion on entropy, relative entropy, etc. is actually from chapter 11 of the book. Okay? And the rest of what I'm going to talk about today will go back to chapter 2. Then of course, there are lecture notes by John Preskill online. Again, chapter 2 talks about the density operator and so on. And chapter 4, I'm sorry, I'm writing this all the way down, talks about entanglement. Many of the things that I'm going to talk about starting the next 5 minutes will be covered in some way in chapter 4 here. Okay? So at least these are what I use as my reference materials by and large. So this I would, yeah, if you're interested in actually proving this and so on, I would urge you to look up chapter 11 of Nielsen Chuang where this is done nicely. Yeah, there was a question. Yeah. I didn't understand. What's your question? Yeah. No, you could, provided their supports are the same, basically, right? Provided their supports are the same. So for example, if both are full rank on the space, then you don't have anything to worry about. You can define it either way, right? So yeah, in most cases you will not have an issue, and that's why this definition is fine. It's only in very special cases where you have to worry about the null space of this that you have a problem, right? Otherwise this is okay. The support is basically the space on which it has non-zero. So it's basically, think of the space spanned by its non-zero eigenstates, right? That's the support. Yeah. I didn't say it was a metric for now. Let me just say that it's a distance measure. It's a measure of how different these two density matrices are, and the reason I say that is simply this, that it is positive, okay, and 0 if and only if the two density matrices are the same. So it gives me a measure of how different they are. Yeah. It is not. Yeah. It is not symmetric, so it is not going to, yeah, yeah. So like I said, you can define other maybe quote-unquote nicer measures maybe, but in an operational setting, this has its usefulness.
Let's say that I understand this is not a metric, so I was thinking you have a one Hilbert space, then in one Hilbert space, how can you have two distributions of Pi and Q1? I mean, you have one system, and what a system I mean.
Yeah, I can write down different density matrices for the same, in the same Hilbert space, no? What is preventing me from doing that? Yeah. Okay. Right? Okay. So now, the reason I introduced all of this was to say that if you now apply this result for any arbitrary density matrix and compare it with your maximally mixed state. So I refer to the maximally mixed state as I by D, right? Because this, when I diagonalize this density matrix, I basically get a decomposition of identity here. This is a set of orthonormal states. So this is I by D, right? This is the maximally mixed state. So when I do this comparison, and this Klein's theorem or Klein's inequality tells me that this should hold, right? And when I simply expand this out, this then gives me the statement that S of rho is always less than or equal to log D with equality if and only if rho is equal to I by D. Okay? So this is one way to sort of show that the maximum of the von Neumann entropy is indeed log D and that it is attained for a maximally mixed state. Okay? So I wanted to introduce this entropy before I move on to talking about bipartite quantum systems, because very soon I want to talk about what's called the subsystem entropy, okay? And then questions like additivity and so on will naturally come into the picture, okay? So I'm going to now move on and talk about how do you describe bipartite quantum systems and start talking about product versus entangled states. Any questions on this part? Yeah, so see if you can, so maybe assume this and see if you can use this to prove this, okay? So maybe this at least is something that you should be able to do, okay? Yeah.
I have a problem in relative entropy. So I have a system. I have defined a density matrix. Now you say that I can define rho and sigma both.
Yeah.
But and those two will be equivalent.
So think about it this way, right? I have a system which is undergoing some evolution, okay? At time t0, its density matrix was this. At a different time, its density matrix was something else. How far away have I moved from this? Okay? Yeah. All right, so let's now change tracks a bit and talk about, so I could in general talk about multi-party systems, but since we're mostly focusing on bipartite, so then maybe until tomorrow at least, let's just talk about bipartite quantum systems. So I now have two So I think of some systems A and B, okay? In a open quantum system setting, for example, this could be the system of interest and the B could be a much larger system which you often think of as the environment or the bath, right? And the question is now, how does one describe states of this joint system or this bipartite system, right? And the way, so if I think of HA as a Hilbert space that this is curly H, not my straight H, which is the Shannon entropy. This is the Hilbert space that I associate with system A, and this is a Hilbert space that I associate with system B. Then the joint system, the Hilbert space that is associated with the joint system, is described via a tensor product of these two systems. Okay? So I have to ask if everyone here is familiar with the notion of tensor product. Yes? Okay. So let's think of a simple example of C2 tensor C2. Okay? So this is just, for example, a system of 2 qubits. Okay? Let's say that I have some standard basis which I label 0 and 1 for the first system. I have another basis 0 and 1 for my second system. I could put little a and b here, but maybe we don't need that, right? Now, how do I get a basis for the joint system, which is 4-dimensional? So I take all possible combinations here, right? It's a 4-dimensional system. So the basis is essentially now 0, 0, 0, 1, and I will soon start getting rid of the tensor product, so I will write joint states like this, and then I may even get rid of the additional angle and the straight line and simply write a state like this. So I hope we are okay with all these ways of writing bipartite states, okay? So By 1, 1, I simply mean a ket 1 on the first system and a ket 1 on the second system with a tensor product taken. Okay? So, good. So, we have 4 orthogonal states, which forms a basis for this system of 2 qubits. Okay? Now, you can ask, what kind of states can I write down for this bipartite system, for this joint system? Okay? So, the most general state is, of course, could be a superposition of all 4 basis states, right? So, I'm going to say an arbitrary state, pure state of this joint system could be of the form alpha 0, 0, beta 0, 1, gamma 1, 0, plus delta 1. Now, the question naturally arises as to whether I can now view this joint state as a state of system A tensored with a state of system B, right? So, the question is, can I write this as some phi A tensor phi B? There could be some states which have this form, but then of course you know that there exist states like this, so I'm going to call this state by a particular name. So I'm going to call this beta 0, 0, which is of this form. Okay, some of you may recognize this state. Yes? Sorry? Bell state or spin singlet state, right? And of course, you know that this state is one of those states which cannot be expressed in this form, right? So, we then have this notion of product states versus entangled states. So, we say that a joint state, joint pure state, I'm only talking about pure states now. A joint pure state is a product state if there exist phi A and phi B such that psi AB can be written like this. But if they do not exist phi A and phi B such that the state can be written like this, then we say that the state is entangled. So, this is the simple sort of definition that you can give to the notion of product versus entangled states. So, if I have a description of this form, means if there exist, so I guess, so let me phrase it this way. So, let me say, do there exist phi A, phi B such that is equal to this, okay? And if yes, then this joint state is a product state. It means that I have an independent description of the state here and an independent description of the state here, and I got this joint system state by actually combining these two local descriptions of the state. So I have a local description of the state of this system, I have a local description of the state of this system, and I simply put them together to get a description of this joint system. On the other hand, if I cannot find these pure states, right, it means that somehow this local description does not exist corresponding to states like this. So I do not have a local form for this state, independent local forms for on each subsystem for this state. So then obviously it tells me that somehow there is some correlation between these two systems when they are in states like this, right? But before getting into that, I want to talk about how do I sort of identify whether, so if I'm given, so remember we said an arbitrary state can be written like this, right? So a general, I'm going to now say 2-qubit state, I hope that's okay. In this case, it was just qubits. So a general state can be written like this. And given a state like that, how do I check or how do I identify whether the state belongs to this category or this category, right? And so let me, for example, give you a particular set of states, and you can tell me whether they are product or entangled. And the answer, of course, comes in the form of something called a Schmidt decomposition, which is what I want to talk about next. So once again, these are with two-level systems. The examples are with two-level systems. So yeah. So I'm going to write down 3 states. Oops. I'm going to say psi 1 is 0, 0 plus 0, 1 plus 1, 1 by root 3. Psi 2 is 0, 0 plus 1, 1 by root 2, the state that I wrote there, which you already know is what's called a Bell state. And psi 3 is this state. So are these states product states or are they not? That is the question. So this one maybe you already know is a Bell state, okay? So how would I check, right? So one way that you can think of is, okay, you go back, you write it like this, okay? So I have some, write down a pure state here, you write down a pure state here with coefficients, and you try to solve for those coefficients, and you see whether you can end up with a consistent solution for that, right? That would be one way of doing this. But what about a state like this? And what about something like this? So I'm going to claim now that this state is actually a product state. And maybe leave it to you to tell me which are those two local states, pure states, whose tensor product is actually going to give me this state. Yeah, so this is what I called, I think, the plus state in the morning. So this is simply plus tensor plus. Okay, and you can check this. So this is a completely unentangled state. This is something that we think of as a canonical example of an entangled state. What about something like this? So is there a systematic way to address this question? And the answer is, when one says that a state is entangled, like this case, right? So I know we'll talk about the CHSH inequality tomorrow and all that, but naively what is one saying? You're saying that there exist some correlations between these two systems. So let me put these labels A and B here. So for example, if I were to measure a spin Z, so let me say that the 0 and 1 are the eigenbasis of the sigma Z observable, okay? And if I make a measurement of sigma Z on the first subsystem, on subsystem A, and I get a particular outcome, then if I make a measurement of sigma Z on the second subsystem, I can only get a specific outcome there, right? These outcomes are correlated. That is what this is telling me. But this state has been written out in a particular basis, and it tells me the existence of correlations in that basis, right? It tells me about the existence of correlations when I make that sigma z tensor, sigma z measurement on this joint state. So the question that one has to ask when one asks, is a state entangled, is also which basis is it entangled in? Okay? And this idea of Schmidt decomposition addresses both of these questions. It says, well, if you want to first check if a state is entangled or not, you should probably express it in that basis. So what did you do here actually? You actually did a basis transformation. You went from the sigma z eigenbasis to the sigma x eigenbasis. And although it looks apparently like there is some correlation, or there is some, that it's not apparent that these systems are uncorrelated, in the sigma x basis it becomes apparent. In the same way, here the entanglement is apparent in the sigma z basis. So the question is, what is this basis in which the entanglement is actually manifest, right? So let me write down the statement of the Schmidt decomposition. So consider a pure bipartite state, psi AB, which belongs to, let me say that the first one is a D1 dimensional space and the second one is a D2 dimensional space. Okay, so let's write down the most general form of this. Okay, so given any pure bipartite state, there exist orthonormal bases. So I'm going to call them EI on subsystem A, okay? I going from some 1 to k. This is an orthonormal basis for the subsystem A, and another basis, some Fj, for subsystem B. Oops. I'm sorry, I want to say here D1 and D2, right? Okay. Such that I can write this joint bipartite state in this form, sum over k, lambda k, okay. So I'm going to say k going from 1 to r, ek, fk, where r is basically smaller than the min of D1, D2, okay? So this is what the Schmidt decomposition theorem states. It says that given any bipartite state, I can always find local bases, okay, in the two subsystems, such that I have a way of writing out this state. Now, what is so different about this way of writing down the state? Normally, when I expand this in these bases, how many terms will I have? This is a D1 dimensional space, this is a D2 dimensional space. I will have D1 times D2 terms. So I have all possible cross terms between these bases, right? That is what I would get if I just did a decomposition in this basis. Normally, right? I'm sorry, not in this, but okay, let me take that back. So I have a D1 dimensional space and a D2 dimensional space, and if I were to just expand this without paying attention to which basis I'm expanding in, I expect to end up with D1 times D2 terms in that expansion, okay? But this theorem tells me that there is always a special basis in A and a special basis in B in which all these cross terms get eliminated, and it is possible for me to express this joint state of the system purely using correlated terms like this, right? You observe that this K index is the same, right? So now you imagine that if I were to make a measurement in this basis in system A and in this basis in system B, these outcomes are correlated. Because if I get a particular index here, then the state here has to collapse to that corresponding index. So the Schmidt decomposition says there exist these local bases such that you can eliminate all these cross terms and end up with a compact description of the state in which these correlations are manifest. Now, how many terms should I have in such a sum? Now, the first system has D1 degrees of freedom, right? That many orthogonal states that it can access. The second system has D2 degrees of freedom. How much correlation can system 1 and 2 have? If you think about that a little bit, you will see where this min of D1 comma D2 comes from. My system A, whichever is the smaller of the two, I am bounded in correlations by that number. There is only so many degrees of freedom that can get entangled between these two systems. And so the number of terms I have in this compact description has to be bounded by the smaller of those two numbers. Okay? And then you can say that, okay, the number of these terms itself, in a sense, tells me how entangled a particular state is. First of all, it tells me whether the state is entangled, and then it tells me how entangled the state is. Why does it tell me whether a state is entangled? So I could imagine a scenario where there's only one term in this sum, like this. So you see, what I've done here is essentially taken an arbitrary expansion in some general basis and gotten it into a Schmidt form, where there is only one term in that sum, okay? Which then means that it's a product state, because there is exactly one state here and one state here, which gives me this joint state. So this is a product state. So what you did within a matter of seconds, very intuitively, to check whether a state is entangled or not, one is systematically now doing this here. And there's a very simple mathematical reason why this is true. Why should there exist these bases where you can actually expand the state in this form? The answer comes simply from something called singular value decomposition. Okay? So I'm going to now tell you a little bit about where the Schmidt decomposition comes from. Is the statement clear? Are there questions? Or is it already, people are lost? Oh, they should. Indeed, they should. Yeah, thanks. So what property do you expect that they should have? So, yeah, let me write that here. So, sum over k lambda k squared should be 1. Yeah, except what is probability in this case? Sum over k lambda k squared is 1. So lambda k squared is something that lies between 0 and 1. Okay? And indeed, this will also become useful in talking about another measure of entanglement that is related to the entropy. Okay? Okay, so why is this true? Why should there exist these bases? So the answer comes from, like I said, something called the singular value decomposition. Everyone here familiar with the singular value decomposition? Yes? No? Okay, so you're all familiar with an eigenvalue decomposition, which basically says that if a matrix is diagonalizable, yeah, there's some matrices which fall into that category, then there exists a unitary. So let me just write down. So if A is diagonalizable, then there exists a unitary U such that, let's say U dagger is D, is a diagonal matrix. Now the singular value decomposition generalizes this idea for arbitrary matrices and says that for any matrix C, there exist unitaries U and V such that U, C, V dagger is, so C could be even a rectangular matrix, for example, nothing constraining it to be square, etc. It gives me a matrix, let me call that S maybe, whose diagonal entries are essentially the, so it gives me a diagonal matrix S whose diagonal entries are the singular values of C. Okay? I am not going to go into proofs of this, but one of the references that I mentioned, which is chapter 2 of Nielsen Chuang, actually takes you through different decompositions which lead you to this. One way of doing it is via something called polar decomposition and so on. This is, I think, a very useful and important result in linear algebra. Unfortunately, many of us don't encounter this normally, which is a pity. But this essentially, it's just this statement. So the Schmidt decomposition, in a sense, is a restatement of the singular value decomposition. And I'll just show you why, and that will complete so-called proof of the Schmidt decomposition. Yeah, so just like how you think of these as some eigenvalues of A, the diagonal entries here, these diagonal entries are called the singular values. Oh, I said there exist two unitaries U and V.
Does it mean that this C matrix cannot be diagonalized using just one unitary matrix?
So when I say something is diagonalizable, it always means that there exists a single unitary matrix which is going to take me to a diagonal form, right? Now there are only some matrices which are diagonalizable. Okay, maybe quiz. What do you call the class of diagonalizable matrices? In physics, what do you encounter? Which are the matrices which are diagonalizable? No? Can you write down a spectral decomposition for all matrices? Hermitian, okay. What about a unitary matrix? Aren't we all diagonalizing unitary matrices all the time? You have a Hamiltonian, you make a unitary matrix out of it, and then you diagonalize it, no? So, what category do unitary matrices fall under? Okay, so there are what are called normal matrices, okay, or normal operators in the operator language sense, which is basically any matrix that commutes with its adjoint is called a normal matrix. And for any normal matrix, you have an eigenvalue decomposition. So the original statement or proof of the spectral decomposition is not for Hermitian matrices or Hermitian observables, it is actually for normal matrices. And Hermitian matrices form a special class of normal matrices where the matrix is the same as its adjoint. Unitary matrices, you realize, indeed satisfy this, that they commute with the adjoint, and they are also normal matrices, okay? But now one is talking about arbitrary matrices, okay? See, the point is, when I have a diagonalizable matrix, there is a special set of values that I extract from it, which are these eigenvalues. There's a special basis that is associated with it. But for an arbitrary matrix, if I want to think in terms of, is there a special form? Is there a special basis from which I can extract some information about this arbitrary matrix? The singular value decomposition sort of answers that question. It tells you that there isn't a single unitary which is going to take you to this form, but there is a left unitary and a right unitary, okay, which allows you to get this into a diagonal form, okay, and these diagonal entries are what you call the singular values of this matrix, okay. And maybe I should point out that, okay, so let me go back to the Schmidt form and say how we use this. Maybe we can discuss this a bit more in the tutorial tomorrow. I hope you wrote down these states, because one of the things after I do the Schmidt decomposition that I would like you to think about is this state entangled or is it a product state? And if it is entangled, then what is the basis in which this is entangled? So essentially, what I would like you to do is see if you can bring it to this Schmidt form, okay? And I'm going to tell you right now how, given an arbitrary state, or I just expand this in some arbitrary basis, how I'm going to bring it to Schmidt form. So please note this down. Like I said, this is part of the homework for tomorrow's tutorial, okay? Okay, so how do I get a state to its Schmidt form? Well, you start by expanding this bipartite state in any old basis, okay? So typically, at least in quantum information and computing, what we do is we think in terms of some standard basis, okay? So for the first subsystem A, let me call this some I going from 0 to, what was it, D1 minus 1, and HB has some other standard basis J going from 0 to D2 minus 1. I'm going to run into some index problems, but that's okay. We can keep changing around the indices. So I'm going to expand this bipartite state in this standard basis. Then this is what it looks like. So I take tensor products of these two bases. That forms a basis for the joint space. This is just the standard expansion. And now you see where the singular value decomposition comes into play. This matrix, this set of coefficients Cij, if I were to think about the matrix whose ijth element is essentially this Cij. So you consider this matrix of coefficients where I have expanded this in some arbitrary basis. Could be any basis, right? And now this is going to be some rectangular matrix, right? It's some D1 cross D2 matrix with no special properties. But I can always do a singular value decomposition of this matrix using a pair of unitaries, U and V, and bring it into a diagonal form where this could be a rectangular diagonal matrix, for example, again, right? But it's a diagonal matrix nonetheless. So I hope you see where the Schmidt form is coming now. I take this matrix of coefficients, I perform a singular value decomposition on it, right? Which means I identify that U and V, which is going to take me to this diagonal form. And now you realize that you have a pair of unitary, a D1 cross D2 matrix, okay? So here I have a D1 cross D1 unitary matrix. Here I have a D2 cross D2 unitary matrix. So this D1 cross D1 is a unitary transformation of the first subsystem. And what does a unitary transformation of a set of basis vectors give me? gives me another basis. Yes, if I were to make a combination of these basis elements with unitary coefficients, I end up with another basis for the same system. Now take the V matrix, that's a unitary matrix for the second subsystem B, which again transforms this into another basis. And now because the Cij has been decomposed into this diagonal form, correspondingly, if I rotate these two bases using those unitaries, I'm going to end up in a form where I have only diagonal elements in this expansion. And these two local bases that you get by performing, essentially you are performing local rotations on each subsystem, and what unitaries you need to use to perform those local rotations you get by doing this singular value decomposition. Okay? And then you basically see that you are in this form where you can now read off the correlations in the state. So the singular value decomposition of this matrix of coefficients identifies for you the basis, the two local bases, which could potentially have correlations for this joint state. Now if it turns out that there is only one, so when I do this, right, so if it turns out that this matrix, now how many singular values does this matrix have? If it turns out that it has only one singular value, one non-zero singular value, then this expansion has just one term, right? Because I hope you realize now that these lambda k are essentially these singular values, these elements sitting in the diagonal here. Okay? I could write down the whole calculation with all the indices. I don't know if you want me to do that. Maybe I can if we still have time, but I'm just trying to give you a feel for this rather than write down all the algebra out here. So if this matrix C has only one non-zero singular value, then there is only one term in this expansion. And that's, therefore, the state is essentially a product state. Yes. So you take, like I said, whichever is the smaller of these two, right? So you only expect to have, if B1 is smaller, you expect to have that B1 cross D1 square, and those will be populated. So the most number of singular values that you can have will be R cross R. So you will have an R cross R square, where R is whichever of these is the smaller one. So you can think of these as being your lambda 1, lambda 2, etc., lambda R, right? These are the coefficients that figure in this Schmidt expansion.
All the elements will be zero. All other elements.
Yes, 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 yes.
One way to talk, one side is it?
Sorry?
It's going to talk one side at least.
Um,
I mean, like this one is D1 cross D2.
yeah. So okay. So let's say it's like this. Yeah. Okay. Yes, absolutely. Yeah. Yes. Yeah, something like this. Yeah. Yeah. Yes, as we say in Hindi, picture abhi baki hai mere dost. So on Wednesday, we will look at mixed states. So we are going from known to the unknown slowly, right? So the problem of pure state entanglement, as you can see, is by and large now solved, I would say, right? For bipartite, you could have also asked me, I restricted myself to just bipartite. It turns out that if I go even beyond a pair of systems to a third system, the Schmidt decomposition doesn't exist. Because here, the singular value decomposition came to my rescue. So I could just take this matrix of coefficients, do a decomposition. It gave me a pair of unitaries, which told me what is the local basis, what rotation should I use on each subsystem, and got me to this nice form, using which I could check whether the state is entangled or not. Now, what do I do if I have a multipartite system? Do I And of course, in a multi-party system, which entanglement am I talking about? Am I just talking about entanglement between two subparts of the system, or am I really talking about entanglement between every part of this multi-party system? So there are various questions that you can ask there, many of which we still do not have the answers for. But as far as pure bipartite systems are concerned, the Schmidt decomposition pretty much solves the problem for you. Right? Yeah, I don't know if this.
Is it the same reason that we are getting non-zero part and rest is zero? Singular word comes from the determinant of matrix is not equal to zero, then we call it a singular matrix.
Probably, yeah.
No, because it's one and not double sum. It's a single sum, not a double sum. There's nothing infinite. There's no singularity. Singular means single summation, not a double summation. That's a miracle.
Yeah, I'm not sure about the origin of that. Yeah.
This decomposition is unique or we can have.
That's a very good question. Now, as far as the singular value decomposition is concerned, it is unique. Okay? So the set of singular values associated with this arbitrary matrix C is unique. Okay? But once I write down this decomposition, it is possible that I could still rotate my local basis, right, and not lose this form. Okay? There exist some states, not for all states. One could think of doing local operations here, local unitary transformations, and not lose this form. Okay? But this set of coefficients here, which in our case we will call them Schmidt coefficients, this is unique because they are simply these singular values here. Okay? All right, so let me say a few more things about this. So now, hopefully I've convinced you that the number of non-zero singular values of this coefficient matrix tells me how many non-zero terms I have here, which in turn gives me a feel for the extent of correlations or entanglement between these two systems. Like I said, the most I can have is the smallest of the two dimensions. So if I have all the way up to D1 terms in the sum, then I would say that this state is actually a maximally entangled state in that sense. So if I have a pair of qubits, for example, each of dimension 2, then what is the largest number of Schmidt coefficients I can have, non-zero Schmidt coefficients? It is 2, right? Because each subsystem is of dimension 2. This C matrix is I have this matrix of coefficients here. This is essentially a 2 by 2 matrix. It can have at most 2 non-zero singular values. And so when I write down my Bell state, as you will recall, it's exactly 2 terms, 2 non-zero terms. So this, I think I call this beta or something, right? So this is a Schmidt form which has as many non-zero Schmidt coefficients as it can have. Okay? So that should tell you that I have in some sense maximized the extent of correlation between these two systems. But so there are 2 ways that you can think of quantifying entanglement from the Schmidt decomposition. So let me erase this part. So one is to ask how many non-zero Schmidt coefficients do you have, and that is called the Schmidt rank of the state. So there is something called the Schmidt rank, which is basically the number of non-zero lambda k. And the second thing that I can do is now, this is still not a very fine measure of entanglement or correlations, right? Because it's only counting how many non-zero terms do I have in this sum, okay? But now I could think about comparing 2 states of this form, right? So I could again do this trick where I have, root 3 by 2 0, 0 plus 1 by 2, 1, 1 versus this state. So how do I compare the entanglement content of these two states? Both of them have the same number of Schmidt coefficients now, right? In this case also there are two non-zero terms. So I hope you realize when I write this that this is in this form, right? My EK is 0 and 1, my FK is 0 and 1. I have no cross terms. So this is a Schmidt form. This is also a Schmidt form. There are no cross terms between these two bases, 0, 0 and 1, 1. Both of them have exactly the same number of non-zero lambdas, okay? But certainly there must be some difference between the degree of entanglement between these two states. How do I quantify that? So a more refined measure of entanglement would be now to actually consider this probability distribution lambda k squared and ask what is the Shannon entropy of this distribution. The more spread out this distribution is, the more entangled you are, okay? The higher this entropy of this Schmidt coefficients is, the more entangled you are, and we'll maybe see this okay. So the Schmidt rank is one thing. Then I'm going to actually talk about okay. So let me say so for now let me just call this the Shannon entropy of the Schmidt coefficients lambda k squared. So I can write down this measure h, let me just call this h, okay, which is minus lambda k squared log lambda k squared, right, sum over k. So of course, once again you see that if there's only one term in this expansion, then this is like having a single pure state, right? So there's only going to be one term in this probability distribution that has zero entropy. The maximum that you can have is as many non-zero Schmidt coefficients, which is going to be log r, right? So sorry, I call this R, I guess, the Schmidt rank. So the maximum this can be is log R, where R is the number of non-zero terms in your Schmidt expansion, right? Now, why is a higher entropy here a signature of greater degree of correlation between these two systems? So let me go back and look at this. So here, like I said, so when you make a measurement on, I mean, I'm just now trying to intuitively say this. If I have this bipartite state, and let's say on subsystem A, I perform a measurement in the 0, 1 basis, right? I get a particular outcome. Let's say I get outcome 0. Then because the state has now collapsed to this part of the superposition, the outcome on the second subsystem must also be 0. How much information am I uncovering by getting this value, by realizing this value? This is an equal superposition of these two states, right? So if, so let me maybe draw a picture like this. So let's say that, so let's bring in some spatial separation between these states in preparation for tomorrow. So let me move these two Hilbert spaces apart, and now they are sharing this, I have this joint state of these two systems, right? This is the standard Bell experiment setting, right? And this is one lab, this is another lab, measurements are being performed here, measurements are being performed here, okay? Now if this lab outcome 0 is realized, then you see that the state must collapse to this 0, 0, right? And if A then communicates that information to B, then the person who's going to do the measurement in lab B knows that they are also going to get outcome 0 here. But before they had that knowledge, they were maximally uncertain about this outcome because this was an equal superposition of 0 and 1, right? So I hope intuitively at least it is clear that both outcomes were equally likely until one of them did a measurement and collapsed the state down. Correspondingly here, because it is no longer this equal superposition, the amount of uncertainty is lesser, or the amount of information that you're extracting upon performing this measurement is lesser. And of course, correspondingly, the entropy associated with that is lesser. So a state whose Schmidt coefficients have lesser entropy has lesser entanglement content than a state where your entropy of the Schmidt coefficients is larger. So I waved my hands around a lot and said this. Is there a precise way to talk about this? Is there a precise way to say why this entropy must tell me something about the correlations between these two systems? The answer is yes. I'll just tell you maybe a couple of minutes what that is, and then we'll, yeah. Yeah.
So could I like think about it in this sense that actually I came to the opposite conclusion in the sense that let's say the first lab, we're looking at the first expression with the root 3 by 2. The first lab measured a 0. So the other lab was expecting a 1, 1 with the probability 1 by 4, but then they were maximally surprised by the fact that it measured a 0, because is that the wrong way to think about it? I mean,
yeah, that is not quite the right way to think about it, because you must ask, what is the state of knowledge that the second lab had to begin with? If I tell you and another person who is in a different lab in this building that somehow I have sent you both these pair of entangled photons and this is the joint state of these photons, right? What is your local description of the state? What is your initial state of knowledge, right? Then post measurement, what happens is what one is asking. But before asking that question, I should have actually asked the question of how do I now describe the state? I've told you that, well, or we all realize that you can't simply describe it as one pure state here and one pure state here. So the answer is, you do have a local description of the state in terms of what is called a reduced density matrix. Okay? So I can take this joint pure state and trace out subsystem B to get I'm not going to get a pure state description, local description, but I will get a mixed state local description. So I have what is called a reduced density matrix. Think of this like a marginal probability distribution, right? If I have independent random variables, then the joint distribution is simply the product of these two distributions. But if I now have correlated random variables, then the way I get to the individual distributions of these two random variables separately is by doing a marginal, right? So we've all done calculated marginals of probability distribution. So this is exactly like that, except you now have to do an operation called a partial trace. So you do a partial trace, you get a reduced density matrix here, you get another reduced density matrix here. So how much information you uncovered or how uncertain you were boils down to how mixed was this density matrix, right? If you were in the extreme situation where both of these were pure states, then both these entropies are 0 and your entanglement is also 0, right? But now if you were in the other extreme where, like I said, you have this equal superposition, then one can show by doing this partial trace, so maybe tomorrow that's where I'll begin, by doing this partial trace, you can show that these reduced density matrices are actually maximally mixed states. Whereas if I had something like this, where I was not uniform superposition of these two states, then my reduced density matrices have lesser entropy than the maximally mixed state, and so the amount of information I am uncovering through the measurement in some sense is lesser, or my uncertainty is lesser. Okay? So that is the sense in which these, so coming back to the Schmidt, so it turns out that these Schmidt coefficients, when you do this tracing out, these Schmidt coefficients will essentially constitute the eigenvalues of these reduced density matrices. And as you know, the Shannon entropy of these eigenvalue distributions tell me something about how pure versus how mixed these states are. And the more mixed the reduced density matrices are, the more correlated or the more entangled is my joint state. So this entropy of this reduced density matrix goes by the name of the subsystem von Neumann entropy. The von Neumann entropy of this matrix, as you know, is the Shannon entropy of its eigenvalue distribution. And tomorrow maybe I'll start by showing you that once you have arrived at the Schmidt form, you trace out each subsystem, you end up with two density matrices for each of these local systems, whose eigenvalues are essentially these squares of these lambda k's. They are these Schmidt coefficients. And so this, what I wrote down as the Shannon entropy of these coefficients, is nothing but the Shannon entropy of the eigenvalue distribution of each of these subsystem density operators. And so this entropy quantifies for me how uncertain I am about the local description, which then tells me how entangled is my joint pure state.
Can we calculate this von Neumann entropy also for this case?
Which case?
You have calculated here Shannon entropy.
Oh, that's what I'm saying. So the von Neumann entropy is the Shannon entropy of the eigenvalue distribution, right? So once I have these eigenvalues, I'm telling you that these eigenvalues are exactly this. And so this Shannon entropy is exactly the von Neumann entropy of both of these reduced density matrices.
So why do we have two concepts of, if they are same?
They are not the same, okay? So they are not the same because, so I can think about situations where I consider mixtures of density matrices, right? And when I talk about mixtures of density matrices, then the von Neumann entropy of that mixture, which has a certain convexity property and so on, you will see that there are lower and upper bounds, which, okay, so let me just say that they are not the same. Maybe I'll show some examples tomorrow of properties of the density matrix where the von Neumann entropy is, it's just one limit of that is the Shannon entropy, where you're looking at it in its eigenvalue decomposition, okay? So maybe let me, suppose you think about it this way, where you have a density matrix which you decompose in terms of some arbitrary set of pure states. We discussed in the morning how the same density matrix could have multiple pure state decompositions. So in a different pure state decomposition, there is a Shannon entropy that you can associate with that decomposition, right? So in a sense, the von Neumann entropy picks out the Shannon entropy of the eigenvalue decomposition and not any of those other Shannon entropies.
So basically Shannon entropy is more general and von Neumann entropy is one of the...
No, I wouldn't, that's not my intention to say that. Maybe we'll discuss this tomorrow, yeah. Okay, so we stop here, yeah. Thank you for being patient.
Okay, so for those who are non-local participants, dinner is again at the same place. What, 6:30 is it? 6:30.